Welcome to the Intro to Text-to-Speech workshop by the University of Waterloo Data Science Club. My name is Victor, and I am a workshop lead at the Data Science Club. And so, just to provide a brief overview, the intended audience for this workshop is intermediate data scientists, mainly because we're going to be going over a lot of simple machine learning components pretty quickly and see how they all come together to form larger models. So if you don't have too much of a background in some of those models like neural networks, CNNs, LSTMs, it might be a little bit challenging to follow along, but we'll try to keep this all at a high level. And if you want to dive deeper into any of the smaller components, we have a lot of YouTube pre-recorded workshops. So feel free to go to our YouTube channel and check those out if you want to dive a little bit deeper into the math. But this workshop is mainly just going to teach you how we can put together simple machine learning components and form some of the state-of-the-art text-to-speech models. And just a brief outline, we're going to review how LSTMs, CNNs, and GANs work at a high level, and then we'll understand how those models combine to form an encoder decoder TTS model. And then we'll finally see in action by using a pre-trained Tacotron 2 model and perform some inference on a text that we'll provide. So let's dive right into it. So most text-to-speech models follow this kind of architecture. It's like an encoder-decoder architecture. So we start with the text, and the end goal is to produce the audio waveform. But for the first step, we pre-process it into linguistic features. So this would be like splitting the text into words, or maybe into characters, or even like phonemes, which are kind of like syllables. And then we'll take those, mainly because the model is able to understand those a little bit better than like one humongous blob of text. And then we'll take those, put it into an encoder, and this will convert it into some latent feature. So this would be some gigantic n by m by o matrix that basically represents the meaning behind the sentence. So we basically take all the meaning out of the sentence and convert it to this humongous numerical array, which will be impossible for humans to understand, but the machine is able to condense it into that kind of a matrix. And then we'll decode it into an acoustic feature, and we'll get back to that and on exactly what that is. And then we finally vocode it into the actual waveform, audio waveform. So now you might be asking, what is an acoustic feature? So we use something called Mel Spectrograms. And to get Mel Spectrograms from the audio waveform, we need to follow a few steps. So here on the left, you can see the audio waveform as some signal that's oscillating up and down. And on the x-axis, you can see the time. And on the y-axis, you can see the amplitude. So, of course, we know that sound is made up of different frequencies, so like high pitch and low pitch sounds. And so we use something called the Fourier transform, which is a mathematical formula that allows us to decompose a signal into its individual frequencies and each frequency's amplitude. So you can see how a signal that is made up of multiple frequencies will be converted into another domain, into the frequency domain, where the x-axis is the frequency, and you have spikes where that frequency is most prominent. So this produces a graph, as you can see on the left, which is called an audio spectrum. And this is, here you can see that like the low frequencies, you can hear there's a lot of the low frequency sounds and very little of the high frequency sounds. So yeah, frequency here is on the x-axis and amplitude is on the y-axis. But you'll notice that we removed the time axis. So, and we know that audio waveforms have like a time component, right? So what we do is we apply this Fourier transform multiple times in short intervals, and that's why it's called a short Fourier transform. And we get the audio spectrogram, which is basically the same audio spectrum, but positioned vertically and then spread out across different timestamps. So here we have time back on the x-axis and then frequency on the y-axis. But here you'll notice that frequency here is now measured in hertz. And the reason why we do this, and hertz is a log scale. So you can see that the numbers here go up exponentially. And the reason why is because humans are better able at distinguishing pitches in a log scale than like actual frequencies. So our notion of pitch is actually on the log scale rather than like the regular frequency scale. And then the colors represent amplitude. So yellow means louder, and the darker colors mean like very little amplitude. So here you can see like the higher frequencies are much lower amplitude, and the lower frequencies have a higher amplitude. And here, again, the scale has been changed. Here we're using decibels. And decibels is also on the log scale, funnily enough. And so we basically converted both the frequency and the amplitude into log scales, mainly because humans are better able at interpreting the log scale rather than actual like periodic intervals, which is kind of interesting. Now, we're almost at the Mel spectrogram. We already have an audio spectrogram. We're just missing the Mel component. And what Mel is basically another scale that we're kind of rescaling our frequency to. And this is because humans, studies have shown that humans do not perceive, studies show that we are better at detecting differences in lower frequencies than higher frequencies. And so you can see that the Mel scale is basically squishing the lower frequencies more together and spreading the higher frequencies out. So for example, we could easily tell the difference between 100 hertz and 200 hertz, but telling the difference between 3000 hertz and 3100 hertz would be much more difficult, even though the difference between the two of them are always still 100 hertz. And so that's why we kind of do the shifting of the scale ever so slightly to match our interpretation of hearing. And it's all because like text-to-speech, right? We want it to sound natural. And for something to sound natural, it needs to be something that humans are used to listening rather than something that seems normal, right? And so if I flip through the two images, you can see that the Mel spectrogram one is like slightly more stretched around the low frequencies. And so that's what the scale is basically doing. And so this is the end result, a Mel spectrogram of an audio waveform. And so just to go back, we can kind of compare the audio waveform on the left and the Mel spectrogram on the right. And so, of course, this is using a Fourier transform, and then a few scale conversions. And obviously, the inverse of that is not linear. So we'll actually need a model to actually convert from the Mel spectrogram to the actual audio signal. So back to the text-to-speech architecture, you can kind of expect that, like all these kind of are part of the exact same model, but we actually split it into two models, where the first half of the model does the pre-processing, encoding, and decoding, and the last part does the vocoding. And this is mainly because the Mel spectrogram is still, although it can be generated from the audio waveform, it's still missing a lot of pieces that the audio waveform has. Some stuff like energy and dynamics that we would need like a separate model to encode. And having like all four of these pieces in the same model makes it a bit too complex, and we kind of lose some information along the way. So that's why we tend to split up this pipeline into two pieces, the encoder decoder part and the vocoder. Yeah, so now let's do some review on some simple model components. So neural networks, convolution neural networks, long short-term memory cells, and generative adversarial networks. So let's start with neural networks. So neural networks is basically lots of individual nodes, and at every single node we have an array of inputs, and we multiply them by their corresponding weights and add all of them together with a bias and feed it to an activation function. And all of this would happen in one node, and then we do that multiple times, as you can see here, and across many layers. And so basically and then the model is basically trying to train these weights so that we can basically pull out certain pieces of the input and then do something about that. So like if finding certain patterns within the input by using certain weights. Yeah. And then we also have convolution neural networks, which are pretty similar in that they multiply weights with the inputs to generate an output. But here, instead of taking every single input at every single node, we apply it only on a sliding window that goes across our input. So here we're using a 3x3, the term is called kernel. So we're sliding this 3x3 kernel across our input. In this case, it's a 2D matrix, and we're applying a weight. You can see them as the red numbers on the kernel. And then at every step, we generate one output. And so usually convolution neural networks are used for like image classification, like classifying a picture of a handwritten digit to the actual digit that it's representing. Whereas like neural networks would be more for like just like classifying some numerical array. And although here you can see that it's a 2D image, we can also just apply this in the one-dimensional case, where we basically take, let's say, like a sliding window of like 5 characters and slide it across our text. And basically at every single step, we generate one output. So that's how we would use convolution neural networks for like language processing. And then we also have long short-term memory cells. So this is kind of, this is based off of like recurrent neural networks, where basically you have the output of a previous step added with the input, not really added, but combined with the input at the current step to produce the output of the current step. And then that is fed into as like the hidden state to the next cell. So basically you have this hidden state that's passing through every single recurrent cell. And this way you can basically take information from previous inputs and then generate output based on the current index and all the indexes previous. So that's why it's called like a recurrent neural network, because we have multiple of these cells and recursing along the sequence. And yeah, recurrent neural networks is mainly for sequence-to-sequence processing. since obviously you can tell that we have like this sequence as the input and we have a sequence as the output, where the output is basically based on the current input and all the inputs previous. But one problem with this, mainly with the 10 each function, is that the inputs closer to the beginning of the sequence tend to get lost by the time we've gone through a number of cells. And so to fix this problem, we introduced long short-term memory cells. And so this is a little bit more complex, but one thing to note is that the output is not the same as the hidden state that gets passed through. So that way, we don't need to modify the hidden state too much, and we can kind of keep the elements closer to the start of the sequence, and they'll still be pretty prominent through these functions as closer to the end of the sequence as well. So it's like an improvement on the recurrent neural network. And yeah, it's long short-term memory cells are pretty popular for sequence-to-sequence processing, more than recurrent neural networks because of that problem. And then finally, we also have generative adversarial networks. These are more of like a model architecture rather than like a concrete model component. And so here we have two networks, basically two models, where the first one is the generator network, and it basically takes a noise vector. This could be some random initialization vector or seed or whatever, and the generator network converts that into an image. Of course, it'll be a fake image because it's generated. And then the discriminator network will take either real images or fake images, and then try to predict whether the image is real or fake. So obviously, if the discriminator is able to tell the difference between the two, then the discriminator network does really well, and the generator network doesn't do very well. But if the discriminator network cannot tell the difference between real and fake images, then that means that the generator network is doing really well, and the discriminator network is not doing very well. So if like after multiple iterations, the discriminator network can't improve, and it's always like a 50-50 guess between real and fake, then we can say that we have a pretty good generator network, and then we can use those to generate, in this case, images, but for our case, it would be like speech and stuff like that. So that's basically it for the simple models. But again, we went over those at a very high level. If you want to dive a little bit deeper into any of them or are still confused about any of them, feel free to look at the YouTube videos posted on our channel or reach out to one of the execs. And we'd be glad to go a little bit more in depth into any of them. But let's jump right into Tacotron 2, which is a state-of-the-art text-to-speech model created by Google, actually. And so here you can kind of see the different components. We have the encoder and, pre-processing and encoder part in blue. We have the decoder part in orange, and like the vocoder part here in green. And so here we just go through the flow. You start with the text. In this case, it's split by characters. And then we feed it to a character embedding, which basically maps every character to some integer ID, mainly because models are better at interpreting integers rather than actual characters. Then we feed it to 3 convolution layers and then a bidirectional LSTM. So a bidirectional LSTM is basically 2 LSTMs stacked on top of each other, where the output of the first LSTM is reversed before feeding it into the second LSTM. And so the reason we do this is because if you think of recurrent neural networks as providing information at the current index and all the indexes previous to generate an output, we can also consider indexes after the current index. So bidirectional LSTM can basically get information from before and after the current index to provide the corresponding output. And so all of this are able to change the text into the latent features that will basically represent the meaning behind the sentence. And then we feed it into what's called an attention block. And so what this is basically when we're trying to decode the latent features, since the latent features basically represent the meaning behind the whole sentence, sometimes when we're decoding, we don't really need to care about the whole meaning. We just really care about a certain section of it. And so, like, for example, like if you're decoding like the last few words, you don't really care too much about the first few words of the sentence, right? Because it's much further away. So the attention basically allows the decoder to focus on certain sections of the latent features while it's decoding. So that way it can be a little bit more concise about exactly what pieces it needs to actually decode and create the Mel spectrograms. So here we take the latent features, and then we feed it through 2 LSTM layers and a linear projection. Linear projection just means like a regular feed-forward neural network, so fully connected layer, and then put that into 5 more convolution layers, and then that produces the Mel spectrogram. And the output of the linear projection, we also kind of wrap it around, throw it through 2 more layers of regular neural network layers, and then that goes back into LSTM. And that's basically because with the decoder, we only have the meaning of the whole sentence. We don't really have anything else. So we need to, at every timestamp, we need to feed it back into the decoder to basically predict the next time step. So it's like a recursive decoding. We always use the previous time step to predict the next time step. And all of that, then once you combine the output of every single time step, you then get the full Mel spectrogram. And then we then feed the Mel spectrogram into a WaveNet, which would be the vocoder, and that would produce the waveform samples. Of course, the WaveNet portion is not trained together with Tacotron 2. Tacotron 2 is only trained with the input text and the Mel spectrogram created from the resulting audio waveform. WaveNet is trained separately, as I mentioned before, with the split between the first part and the second part. And that's basically it for Tacotron 2. We can then look at Deep Voice 3, which is a pretty similar model, except this one was created by Baidu, which is China's equivalent of Google, since China has banned Google. But anyways, it's a pretty similar process where we have the encoder part on the left and a decoder part on the right, and then we have the vocoder part on top here, which generate the waveform samples. So we take the text embedding, we feed it through a regular neural network, and then we feed it through n convolution blocks. So this one doesn't use LSTMs, it just uses a massive array of convolution blocks. And then we feed it through another neural network, regular neural network, and then feed it to the decoder, which is basically n copies of attention blocks and convolution blocks. So yeah, this is basically focusing on convolutions rather than LSTMs. And then the output of the decoder can be fed to a multitude of different places, depending on which vocoder you're using. So if you're using the Griffin Lim or the World vocoder, we can create like specific converters that will convert the output of the decoder to something that those vocoders can understand. Or, or with a similar wavenet, we can just generate the Mel spectrogram and then feed it to wavenet to generate the waveform samples. And obviously, with the whole recurrent portion of it, we take the Mel spectrogram output and we feed it back into as the input to the decoder through another neural network, which will then help it predict the next time step. Here we also predict the stop token. This is also in Tacotron 2, it's just not in the diagram that I had, where basically the decoder, since it's using its previous input to predict the next output, this could technically go on like forever because there's nothing telling it when to stop. So that's why we also need to predict a stop token. And what this is basically, after it passes a certain threshold, then we basically decided that we are now done. And so then the decoder will no longer predict any more output, and then we'll stop there. And this is especially necessary when we're training with multiple different length texts. And even with like the same length text, sometimes like the audio version of that text would be different lengths. So that's why we need the stop token prediction to be able to tell, even if the audio file is like 10 minutes for every single output, some of them might actually only be 3 minutes, depending on where the stop token passes that threshold. And so we also have a speaker embedding, and this is kind of like an extra feature where if you want to have different voices, so I don't know if you guys use Siri or whatnot, but like you could probably customize like the voice that is used for Siri. And so you could do kind of like the same thing by passing a speaker embedding to certain portions of the network, and then train it so that like depending on which speaker you want to use, then we can produce like the corresponding output. Of course, that has nothing to do with the text, since the text stays the same. So that's, the text stays normal. And yeah, now we'll look into an actual vocoder. So MelGAN is a vocoder. It basically takes the Mel spectrograms and then converts them to raw waveforms. And MelGAN, as obviously in the name, it's a generative adversarial network. So on the left, you see the generator portion, and on the right, you have the discriminator portion. So for generating the waveforms, we pass the Mel spectrogram through a convolution layer, and then multiple upsampling layers and dilated convolution blocks. So the reason why we need upsampling layers is mainly because convolution layers tend to decrease the dimension of the input. So the outputs are usually smaller than the inputs, and a raw waveform tends to have much more features than the Mel spectrogram. So we kind of need these upsampling layers to provide those more features. And like a simple upsampling layer could be like, if you have like an array of like 1, 2, 3, 4, the upsampling layer, a 2 times layer could be like would convert it to 1, 1, 2, 2, 3, 3, 4, 4, something like that. Basically duplicating the input, and then through more convolution layers, those will change and actually form the output. And what a dilated convolution block is basically, instead of just having a sliding window of adjacent features, we can actually dilate the features where we take inputs at certain intervals behind the current index. So here you can kind of see a 3 hidden layer dilated convolution block kind of in action. And that's how it's used to generate the sequence. And WaveNet that you've seen before is also using this kind of an architecture, but focusing a little bit more on this to actually produce a sequence rather than regular convolution layers. But anyways, yeah, and then it's called a residual stack because we actually add the input to the output of the dilated convolution block, and this is mainly having to do with like gradients and how that's how like certain gradients tend to disappear, gradients which are used to like train the model. So that's just part of the math that goes on behind the scene. And then we also have the discriminator block. So this is kind of the reverse. We take the raw waveform, and the output for discriminator would be whether or not this waveform is real or fake. So we have this discriminator block, which has a few lots of convolution layers and the downsampling layer. It's just a standard kind of classification kind of structure. We also do some average pooling and convert like we apply average pooling on the waveform a few times, and this is just to reduce some of the noise, mainly because like the audio waveform that is produced tends to have quite a bit of noise. So sometimes when we average pool it, we can reduce the noise, and then the discriminator block is better able to distinguish whether it's real or fake, rather than like relying on how much noise is in the waveform. And yeah, so that's MelGAN. So now let's get into an actual notebook and see one of these models in action. So here I've created this notebook, which starts off by kind of describing the Tacotron 2 model and MelGAN, which are the two that we're going to be using for inference. I guess like before that, yeah. I'm not sure if you guys have any questions, but feel free to post in the chat if you do. And yeah, some of the components that we kind of went over quickly, like the location-sensitive attention or like residual connections, they are you can find them in a little bit more detail in like Alvin or Jesse's reading groups. They kind of dive a little bit more into the actual math that goes on behind the scenes for some of these blocks. So feel free to look at the recordings or attend some of their reading groups if you're interested in the math behind some of those components. But yeah, so we'll get into actual inference. So here we'll just start this running, but we'll import a few packages. So we'll import Tensorflow, and we'll use Tensorflow TTS. So this is an open source project on GitHub. You can kind of see it here, and I'll just read the first line. Tensorflow TTS provides real-time state-of-the-art speech synthesis architectures, such as Tacotron 2, MelGAN, a few different state-of-the-art models. And so they provide a lot of these models, and I highly recommend you to look at this open source project, take a look at how they implemented some of the models, and play around with them. It's their documentation is pretty good, so feel free to take a look at that on your own time. And so we'll be using their models, their pre-trained models, mainly because like training them during the workshop would take forever. So we'll just use their pre-trained models to do our inference. And then we also import this dependency that TensorFlow TTS uses, but doesn't really install automatically. So that's just a separate thing that they have to fix. But anyways, Then we'll also import a few packages that we'll actually use in this notebook. So we'll use NumPy to manipulate arrays, to create and manipulate arrays, and then we'll use matplotlib to draw some graphs, and then TensorFlow, obviously because the whole project is in TensorFlow. And then we'll also import TF AutoModel, which we'll use to download the pre-trained models, and then AutoProcessor, which is the same thing but downloading a preprocessor. And then we'll also import IPython display, which will allow us to listen to the audio as a NumPy array from the Google Colab. And then here we'll actually download the pre-trained models. So I'm basically just specifying the from pre-trained. The processor, I'm importing the Tacotron 2 processor. Using the auto model, download Tacotron 2, and I download the Mel GAN. And here you can see this LJSpeech. And what LJSpeech is, oh, I copied something weird. LJSpeech is the kind of like the de facto speech data set. So if you think of MNIST, MNIST, data set as like the de facto data set for image classification, LJSpeech is like the de facto data set for text-to-speech. So it has 2.6 gigabytes worth of text and the audio version of that text. Of course, you can use it for text-to-speech and speech-to-text. Both ways work, and other kinds of stuff on the data set. But anyway, so yeah, these three were trained on the LJSpeech dataset, and that works for our situation, so we'll just use those. And then we just set up a few configurations. These are the default configurations for Tacotron 2, and then we display a summary. So here you can kind of see the encoder portion, the decoder cell, postnet, and the residual projection. You can see that the number of parameters is humongous. There's so many parameters. So it's not a simple model for sure, but you can, as we did, we can break it into some of the components and kind of see how they kind of piece together. But for sure, it's still a very complex model, and it would probably take quite a long time to train. So we're not going to do that here. But anyways, so now let's get into an actual inference. Did the stream go silent? I'm not sure. Can you guys still hear me? Okay, it seems like, okay, cool, awesome. So we'll just continue. So here we're going to use the sentence, Bill got in the habit of asking himself, is that thought true? And if he wasn't absolutely certain it was, he just let it go. So we'll first pre-process it to convert the text into their IDs, and then we'll just take a look at the IDs. So we'll just convert it to a string just to make it look a little bit pretty. So here you can see like 39 corresponds to B, 46 corresponds to I, 49 corresponds to L. So Bill is the first 4 characters of the input IDs. So, and then 11 is the space. So you can kind of see how every single character was mapped to its corresponding identifier as an integer. And then one thing that's interesting is we can examine the lengths. So if we do the length of input IDs and the length, compare it with the length of the input text, you'll notice that they're not actually the same. And the reason for this is because the input text contains 2 quotation marks, And if you think about when you're speaking, you don't really say quotation mark, right? I mean, maybe you do, but like in this case, the processor, we kind of omit the quotation marks here. So we actually remove these two quotation marks, and the input IDs also has one last token, which is unique to it, which is a stop token. So that's 148 here. Um, and so that's why input text has one more length than the input IDs, because it's plus two quotation marks minus one stop token, end token, I should say. And so then we'll feed these into Tacotron 2's inference mode. But before that, we need to convert them to tensors, because TensorFlow can only kind of operate on tensors. And another thing is that we need to convert them to batches, because it's used to like doing multiple batches at the same time. And here we only have one input. So let's define a function here called makeBatch. And it'll take in some numpy array, and then we're just going to return TensorFlow convert to tensor x, and we'll say data type is TensorFlow.int32. We'll just use 32-bit ints, and so that converts the array into a tensor, and then we need to make it into a batch. So we need to increase its dimension, one layer of dimension. So we'll do TensorFlow.expand dims, I think, and then we'll at the 0th axis. So basically, we're just wrapping it in another array. So instead of like, in this case, it's length 125. So instead of it having the shape of 125, it'll be a shape of 1, 125, where the first dimension is the batch dimension, and the second dimension is the length of the text. So now that we have this helper function here, we can do new input IDs is equal to make batch input IDs. And then for inference, we need input IDs. We also need input lengths. So mainly, again, because it is used to it's used to like doing multiple batches where the text in each batch the text in each batch might not be of the same length, so we need to specify the length of each element in our batch. So we'll just make batch and just give it the length of our input IDs. So again, it would just be one array containing just the length of the input, 125 in this case. And then we also need speaker IDs. And so this is basically, again, because Tacotron 2 can be changed to do like multiple speakers, but in this case, we'll just use a default speaker. So we're just going to use 0 here. So now that we have that, we can put this through the inference, through Tacotron's 2 inference. This will then produce 4 outputs: the decoder output, the Mel output, the stop token prediction, and the alignment history. And we'll kind of look into those later. So, and then we'll take the Mel outputs, these are the Mel Spectrogram outputs, and then we'll feed that to MelGAN to produce the audio. And then we'll use IPython display to actually hear the audio. And so I could play this here, but you wouldn't be able to hear it over Twitch. So I've downloaded this this file, and then I'm going to play it back so you guys can hear what it sounds like.
Bill got in the habit of asking himself, is that thought true? And if he wasn't absolutely certain it was, he just let it go.
So hopefully you guys heard that. I mean, if not, I'll be sharing the Python notebook with you all later, and you guys can listen to it yourself. But anyways, you can probably tell, if you did hear it, you could tell it was pretty close to to the text, and I mean it is the state of the art model, so it does pretty well. But anyways, so that's all you need to do for inference, right? You just take the text, you pre-process it, feed it through the Tacotron 2, feed that output to Melgan, and then you got the audio. And that's pretty cool. So now let's actually explore the parts like how the data has transformed at different steps of the model. So we already saw the output of the pre-processing, right? It's the list of IDs here. But let's look at the latent features, so the result of the encoder. Now, one thing that the encoder needs is an input mask. And so one input mask it's kind of like the input lengths, but it's more of like a true and a false array where it's true whenever we're still in the input and false when we're outside. So again, this has to do with like batches having multiple different lengths. And so we're going to say the input mask is going to be a make batch of, and we just basically want an array where it's true for the length of the input IDs. And yeah, since the length of every single element in our batch has the same length of input IDs, we don't actually need any false values in the for, because the length of this array is going to be exactly the same as the one that we need. But anyways, so we'll run that. Oh yeah, I need to do a length here. And then, yeah, so we get this humongous array. In this case, it's a shape, it has dimensions 1 by 125 by 512. So the first one is the batch dimension. So since we only have a batch of one element, that's why it's just one there. And then 125, if you remember, that's the length of our input. So here actually, so that's basically for every single character we have some, so that's like the length of the input. Every single character has this 512 dimension vector. So it's just this humongous matrix, and you, by no means do I expect you to be able to understand what this array of numbers mean, but just know that this is like the mathematical meaning behind Bill got in the habit of asking himself that whole sentence. And so yeah, that's what the encoder part looks like. Nothing too interesting. But here we can also look at the attention. So remember that attention is basically how the decoder focuses on certain elements of the encoder, of the encoded latent features. And so you can see that it's like a generally smooth line from bottom left to top right. I mean, that makes sense because the encoder time step and the decoder time step should be roughly the same. Although notice that there's kind of this smudgy area around decoder time step 300 or encoder time step 60. And so we can kind of examine what's going on there, or like what part of the text is going on there. So if we do input IDs, no, we want the text actually, because we can actually understand the text. And I mean, the two of them are offset by just one. So it shouldn't be too bad if we just take like 5 characters before and after index 60. And so you'll notice right smack dab in the middle, you have this question mark. And I mean, that kind of makes sense, right? Because if you're talking and then you hit a question mark, you'll pause for that many seconds, a few seconds. And so that's why you have this horizontal smudge there. So that's because the decoder isn't really progressing through the latent features. It's just kind of taking a pause there. And so you can kind of see through the attention alignment, you can kind of see that in action here. But yeah, so we can also look at the Mel spectrogram that's being output. And yeah, I mean, there's not too much interesting going on here, mainly because we can't really understand what the spectrogram looks like. But I mean, again, around decoder time 300, we have this kind of pause right after the question mark, right? Whereas like all the other places are relatively filled in with frequencies of different kinds of frequencies. But yeah, and then we can also look at the stop token prediction. So we can do plot. We'll look at the stop token prediction. I think it's 0 because we need to get rid of the batch dimension. Yeah. So here you can see it just kind of sitting around like -15, -20, and then right at the end, it kind of just shoots up. And so that's how the decoder knows, okay, I can stop now because I've basically predicted that I'm done. So then the decoder stops. And so, yeah, that's basically it. And then we can do like the exact same thing with a different kinds of models. So here we can use like fast speech 2 instead of Tacotron 2, and then we can use multiband Melgan instead of Melgan. Here we have input IDs. We basically convert this text, and then we throw this into the fast speech 2 inference. Of course, this one requires a little bit more configuration kind of stuff. Not as simple as Tacotron 2, and then similarly we do Melgan inference, and then we generate the audio. But so the open source project makes it really simple to be able to do this kind of inference. And yeah, so I highly suggest you guys to, if you have time, to just kind of play around with some of the models that they provide, maybe train your own version, or like import their models, but like train it yourself, just kind of see it in action or whatnot. But yeah, so that's basically it for that. Just one last slide. Just like the kind of encoder decoder architecture is pretty prevalent across machine learning. You can use it for like translations. So instead of like converting text to speech, you can convert it from like English to French, right? And I mean, like the architecture is kind of similar, right? Because you can encode the meaning behind it from the English perspective, and then decode it into the corresponding French sequence of text. And then you also have like other transformer models like BERT for more like natural language processing. And you can also do like image captioning. So this one's a little bit more obscure, but you can kind of think of it as like we feed it an image, and then it encodes the image, and then decodes it into a sequence of captions that you could use to caption the image. And yeah, so multiple different, this kind of encoder decoder architecture is pretty common across multiple different types of machine learning models. So you will by no means, it's by no means just limited to text to speech. So hopefully this was a pretty good introduction to encoder decoder models, as well as specifically text to speech models. And yeah, if you have any feedback, please fill out the feedback form. This is also like the first time we're streaming this on Twitch, so try to post this in the Twitch chat. Okay, yeah. This is our first time streaming on Twitch, so if you have any feedback as to whether or not this worked, whether or not we should go back to Google Meets, or try something else, maybe like Discord or something, please feel free to put that in the feedback form, as well as anything else, whether or not you liked it, anywhere we can we can improve or whatnot.